There's an interesting thing about electricity. You can't see it. The electrons that make up electricity are thousands of times smaller than atoms. Yet their ability to generate magnetic fields and turn into so many different forms of energy makes them extremely valuable. The flow of electricity through circuits must be precisely controlled. This is nowhere more important than in electronics, where a fluctuation of a millivolt or a microamp can cause programs to be lost, information to be misdirected, and cost someone a lot of time and money, not to mention aggravation. Monitoring the flow of this invisible form of energy is the job of electrical transducers. Electrical transducers detect electrical current and represent it as some kind of output signal. The output signal could be the mechanical movement of a needle, a digital readout, or a series of light-emitting diodes. You've actually been using electrical transducers all along in this project, your volt-ohm meters, or VOHMs, and your digital multimeters, or DMMs. Your volt-ohm meter is like a small electric motor. A coil rotates between two magnets. We saw in Unit 10 how a coil with a current passing through it will spin when it's placed in a magnetic field. If the coil is held by springs, it will only be able to push against the spring and move a small amount. That's how the meter works. A magnet surrounds a coil to which a needle is attached. The needle shows the amount of rotation of the coil. That rotation depends on the amount of current passing through the coil. So an electric input has now been changed into the mechanical action of a needle. Meters are used to measure both voltage and current. And like all good transducers, they use very little electricity in the process. Here's how the voltmeter does it. The meter has very high resistance, so only a small amount of current will pass through it. The rest remains in the circuit. The object is to allow just enough current through to measure the voltage difference across the points where the meter is connected. An ammeter is almost the same thing, except you have to insert it right into the circuit, and it has an extra part, a shunt, which has very low resistance, and it acts like a shortcut. The electricity now has a choice of two paths, one of very high resistance through the coil, the other of very low resistance through the shunt. Naturally, most of the electricity takes the easy shortcut through the shunt and goes back into the circuit undisturbed. Only a very small amount of current passes through the coil, just enough to move it. If the coil has 10 times more resistance than the shunt and it reads 1 amp, then you know that 10 times more current, or 10 amps, have passed through the shunt, and therefore through the circuit. Multimeters have several shunts, so you can choose the resistance and measure a wider range of currents. There's another simpler way of measuring current, which technician John Conrad uses when troubleshooting his electronic equipment.
There are other ways of measuring current or amperage in a circuit without having to be obtrusive and break the wire and insert a shunt. This is one example of them here. Essentially what this is a coil of wire, the hole through the middle of it, but it's one that I can break. So I can slip this around an existing wire like that. Now the way that this works is a wire with current flowing through it generates a magnetic field around itself. This coil turns that magnetic field into a small electrical current of its own, which can be measured by a voltmeter. In this case, we're seeing without the wire through it, there's no current flowing through this loop. With the wire through it, there's roughly 0.6 of an amp flowing through this loop. This is a large measuring device. This is used for measuring larger amperages in the 1 amp to 30 amp range, things like that. But there are smaller devices that are used for measuring smaller currents. This is the exact analogy of this, only the hole, as you notice, is very much smaller. It's designed for going into the innards of one of these TV sets and, say, clipping onto one small wire and finding out what's happening there. Both of these sensors are nice in that we don't have to break the wire to measure the current, but also they take very little energy from the wire that you're measuring, which means that you can go in and troubleshoot a system like this without affecting the system that you're troubleshooting. In fact, there's no way for me to see, taste, touch, or feel the electrical currents or voltages inside this TV set without sensors like these. These translate the voltages and everything into readings on meters that allow me to see exactly what's going on and troubleshoot down to the point of being able to fix what's wrong with the TV set or adjust it to where it works properly.
There's one other electrical transducer that is related to the crystal we saw in the mechanical program. We saw how certain crystals produce electric currents when they're deformed as a force acts on them, the piezoelectric effect. This effect is reversible. In other words, if a current is applied to a crystal, it will change shape or vibrate. This is called the converse piezoelectric effect. These transducers are used to produce ultra-high frequency sound waves, or ultrasound, that are used to image internal organs, like this horse's heart. Electrical transducers are as important to an electrical technician as a screwdriver and wrench are to a mechanic. They provide a picture of how this invisible form of energy called electricity is behaving within complex technology.